Section 7.2, Exponential Change and Separable. The outline of this video is as follows. We will begin by introducing the fundamental concept of exponential change, which is a powerful idea that describes any quantity whose rate of change is directly proportional to its current size. Next, to give us the tools to work with these models, we will learn how to solve a specific class of differential equations called separable differential equations. Once we have established this mathematical foundation, we will put it to use by exploring several classic modeling applications. We will see how a single underlying principle can describe the dynamics of unlimited population growth, the predictable decay of radioactive elements, and even the way a hot object cools in a room, a process known as Newton's law of cooling. This path will show you how to move from a core mathematical idea to solving practical problems in the natural sciences. Let us explore the principle of exponential change, where a quantity changes at a rate directly proportional to its current size. We capture this idea mathematically with a differential equation. The derivative of a quantity y with respect to time t equals k times y. Here, the number k is called the rate constant, and it determines the speed of the change. If k is greater than 0, the quantity undergoes exponential growth, while if k is less than 0, it experiences exponential decay. For instance, in a savings account with compound interest, a larger balance earns more interest, accelerating its growth. To pinpoint a specific outcome, we must also know the starting amount, which we call the initial condition. Y equals an initial value, y naught, at time 0. This differential equation, combined with its initial condition, forms an initial value problem, which is the complete framework for modeling exponential change. Let us derive the solution to the exponential change equation, which gives us a powerful formula for modeling growth and decay. First, I rearrange the equation by separating the variables, grouping all terms involving g on one side and all terms involving t on the other. Then, I integrate both sides, which results in the natural log of the absolute value of y equaling k times t plus a constant of integration, c1. To solve for y, I exponentiate both sides, simplifying the expression to y equals a new constant a times e to the power of kt. The final step is to apply the initial condition that y equals y0 when t is 0, which reveals that the constant a is simply our starting value, y0. This process gives us the final solution, the law of exponential change. Y equals y0 times e to the power of kt. Here we can visualize the solution for exponential change, which describes how a quantity grows or shrinks over time. The graph on the left shows exponential growth, which happens when the rate constant k is a positive number. Notice how all curves start at the same initial value, naught, but a larger value of kong, like 1.3, creates a much steeper, faster-growing curve. The graph on the right shows the opposite case, exponential decay, which occurs when the constant k is negative. Again, the change is more rapid for a clay with a larger magnitude, like negative 1.3, causing the quantity to decrease toward 0 much more quickly. So do not confuse the sign of clay, which determines growth versus decay, with its magnitude, which determines the speed of that change. The key takeaway is that the rate constant ESC controls both the direction and the pace of exponential change. Let us explore a powerful technique for solving a special class of differential equations, known as the method of separation of variables. A differential equation is called separable if we can algebraically rewrite it. So the expression for dy dx is a product of two functions, one that depends only on x and another that depends only on y. The strategy is a straightforward two-step process. First, we rearrange the equation to gather all terms involving y, including the differential dy on one side and all terms involving x, including dx, on the other. For instance, if dy dx equals the quantity 1 plus y all times e to the power of x, we would divide by the quantity 1 plus y to group it with dy. Second, after separating the variables, we simply integrate both sides of the equation independently. This method effectively transforms a single differential equation into two standard integration problems, one for each variable. Let us apply our method of separating variables to solve our first differential equation. The problem is dy dx equals the quantity 1 plus y times e to the power of x. Our first step is to get all terms involving y on the left side with dy and all terms involving x on the right side with dx. To do this, we divide by the quantity 1 plus y and multiply by dx. This gives us the separated form dy over the quantity 1 plus y equals e to the power of x times dx. Now we simply integrate both sides. The integral on the left is the natural log of the quantity 1 plus y. And since the problem states that y is greater than -1, this term is always positive. The integral on the right is e to the power of x. We combine the constants from both integrations into a single constant c. The final result gives the solution for y as an implicit function of x. Let us now apply our model of exponential change to understand how populations grow under ideal conditions, which forms the basis for more complex ecological models. We start with a key assumption. When a population has unlimited resources and no predators, its rate of growth is directly proportional to its current size. This relationship is described by the differential equation dy dt equals k times y, where the constant k is a positive number representing the growth rate. The solution gives us a formula for the population size, y of t, at any time t. It is equal to the initial population, which we call y0, multiplied by e raised to the power of the quantity k times t. For example, a yeast culture in a lab with plenty of nutrients will initially grow this way. The essential point to remember is that under these unlimited conditions, population size increases exponentially over time. Let us apply our exponential model to a decay problem to see how long it takes for a disease to decline to a certain level. We begin with our standard equation, y of t equals y naught times e to the power of kt, and set the initial number of cases, y naught, to 10,000. The next step is to find the specific decay constant, k. Since the cases are reduced by 20% in 1 year, we know that 80% remain. We use this fact, that y of 1 equals 8,000, to solve for k, which is the natural log of 0.8. Notice that stack is negative, which is what we always expect for a quantity that is decreasing over time. And finally, with our complete model, we set y of t equal to 1,000 and solve for the time t, which is about 10.3 years. The process is always to use an initial data point to find the rate constant before solving for the unknown. This graph provides a clear visual for our disease reduction model, making the idea of exponential decay much more intuitive. On the vertical axis, we start with 10,000 infected people at time 0. As time progresses along the horizontal axis, the curve drops, showing the number of cases decreasing. Notice how the curve is steep at the beginning and becomes flatter over time. This shape illustrates a key property of exponential decay. The number of cases falls most rapidly when the infection is widespread, and the rate of recovery slows as fewer people remain sick. For instance, we can see the point where the cases drop to 1,000, which our calculation showed takes just over 10 years. The main takeaway is that this curve shows a process where the rate of change is always proportional to the current amount. Let us apply our exponential model to radioactive decay, a process that is fundamental to fields like geology and physics. The guiding principle is that the rate of decay is directly proportional to the number of radioactive nuclei present. This gives us the familiar differential equation, but with a key difference. dy dt equals negative k times y, where the negative sign shows the quantity is decreasing over time. The solution is y of t equals y naught times e to the power of negative kt. We can characterize this decay with a very useful value called the half-life, which is the time required for exactly half of the substance to decay. It is calculated as the natural log of 2, all divided by the decay constant, say. For instance, radon 222 has a half-life of just under 4 days. The key takeaway is that the half-life is a unique and constant fingerprint for each radioactive element. Now, let us apply our understanding of exponential decay to a practical example. Carbon-14 dating. Our goal is to find the age of a sample where 10% of its radioactive carbon has decayed. First, we use the known half-life of carbon-14, which is 5,730 years, to find the decay constant K. This constant is calculated as the natural log of 2 divided by the half-life. Next, we set up the specific decay equation for our samples. Since 10% has decayed, 90% remains, so y of t equals 0.9 times the initial amount, y naught. This means that 0.9 must equal e to the power of negative kist. Finally, we solve for the time, st, by taking the natural log of both sides and substituting our value for k. This gives us an age of approximately 871 years. So, by measuring the remaining radioactive material, we can calculate how long ago an organism died. Let us now apply our model of exponential change to a common physical process known as Newton's law of cooling. This law explains how an object's temperature changes when it is placed in an environment with a different, constant temperature. The core idea is that the rate of change of the object's temperature is directly proportional to the difference between its temperature and the surrounding temperature. This relationship gives us the differential equation dH dt equals negative k times the quantity h minus h sub s, where h is the object's temperature and h sub s is the constant surrounding temperature. By solving this, we find that the temperature difference, which is h minus h sub s, decays exponentially over time. For instance, a hot cup of coffee cools very quickly at first when its temperature difference with the room is large, but its cooling slows as it approaches room temperature. The key takeaway is that the temperature difference between an object and its environment decreases exponentially. Now let us apply our cooling model to a practical example to see how we can use it to make a prediction. First, we set up the equation for the egg's temperature using the initial value of 98 degrees and the surrounding water temperature of 18 degrees, which gives us the formula h of t equals 18 plus 80 times e to the power of negative kt. The next step is to find the specific cooling constant, K, for this system. We use the data point that the temperature is 38 degrees at 5 minutes, which allows us to solve for K, finding that it equals 1/5 times the natural log of 4. With this value for A, we can find the total time needed to reach our target temperature of 20 degrees. Solving the equation h of t equals 20 gives a total time of about 13 minutes from the start. Since the question asks how much longer it will take, we must subtract the 5 minutes that have already passed. This shows how an intermediate measurement let us calibrate our model to predict a future state, giving a final answer of about 8 more minutes. Let us bring together the main ideas we have covered about exponential change. The central concept is that many quantities in nature change at a rate that is directly proportional to their current amount. We model this relationship with the differential equation dy dt equals k times y, and we found its solution is the function y equals y naught times e to the power of kut. This type of equation is a classic example of a separable differential equation, which we solve by separating the variables onto different sides of the equation and then integrating each side independently. This simple model has powerful applications, describing exponential growth in populations when the rate constant q is positive, and the exponential decay of radioactive materials when q is negative. The key takeaway is that this simple rule about proportional change gives rise to the ubiquitous exponential function that describes so many natural processes. Let us check our understanding of how to set up these exponential change problems. For the first question, involving the bacterial culture, we are modeling exponential growth. The key idea is that the rate of population change, dp dt, is proportional to the current population, p. This gives us the differential equation dp dt equals k times p. The problem also states that the culture starts with 200 cells, which provides our initial condition. P of 0 equals 200. For the second question, about the cooling coffee, we need to find the constant ake. We would start with the general solution for Newton's law of cooling and substitute the known values. The room temperature is 20, the initial temperature is 90, and the temperature at 10 minutes is 60. This creates an equation where ake is the only unknown, which we can then isolate and solve for using the natural logarithm. The main takeaway is that we use the initial conditions and a later data point to find the specific constants for our model.